Okay, for this set of exercises, we're looking at verification by substitution. And for what we have in the case of the equation y prime plus 2y is equal to 0, we're looking at verifying that y equals 3 times e to the negative 2x is a solution. Okay, so just looking at what we have here. So we're looking at y prime and 2y. And so we have with y is equal to 3 times e to the negative 2x. And that will be used to substitute for the y into y. And as for y prime, so again we have for y prime, this is in reference to the change in y with respect to that in x. Okay, so you're looking at d over dx, that which represents y. So for taking the derivative in x of 3 times e to the negative 2x, and I'm going to string this out a bit further. Okay, so I can just move the constant 3 out to the front. So you have 3 times the derivative of e to the negative 2x. And for what we have for e to the negative 2x, okay, so the derivative of e to the negative 2x okay, so we have for the power, okay, you have negative 2x, which is going to have a derivative of 2. So just, you can just extending this a bit, so you have e to the negative 2x times the derivative in x of negative 2x and of course the derivative of negative 2x is negative 2, and coupling with e to the negative 2x, and it's going to turn out that the derivative of e to the negative 2x will be negative 2 times e to the negative 2x. And just for single variable expressions, it's quite obvious, okay, but once you look into multivariable expressions, okay, it's going to require a bit of focus, especially if you have taken Calculus 3 or are about to take Calculus 3, especially working with partial derivatives. You had to be careful with the variables and corresponding degrees. Okay, so for the derivative of 3 times e to the negative 2x, okay, so you have 3 times the derivative of e to the negative 2x, and again, so we have negative 2e to the negative 2x, and so y prime will end up at negative 6 times e to the negative 2x. And going back to what we have for our equation, okay, so you got y prime, again you have negative 6 times e to the negative 2x, and we have plus 2y, again where y we have at 3 times e to the negative 2x, is equal to 0. So here we have negative 6e to the negative 2x, and plus 2 times 3, which is 6. Then we have times e to the negative 2x. Again, the right-hand side of the equation is 0, and guess what? We have additive inverse terms on the left-hand side, and they're going to cancel each other. And it's going to turn out that we have 0 equal to 0. And with both sides balancing, it's going to turn out that indeed y equals 3 times e to the negative 2x is a solution. Now looking at number 7, we have a second order differential equation. And again, we're just going to be looking at the second portion. Okay, now for number 7, we have a second order differential equation. And I said to be checking only e to the x times the sine of x and determining whether that is a solution. So with what we have in the layout, okay, so if I set y equal to y sub 2, okay, so you have y sub 2 is equal to e to the x times the sine of x. And for the first and second order derivatives, okay, so if I go to y sub 2 prime, so I'm taking the derivative with respect to x of e to the x sine of x. So I'm be looking at taking the product property of derivatives. Okay, so we can say we have e to the x times the derivative in x of the sine of x, and we have plus the sine of x times the derivative in x of e to the x. So we have for the derivative of the sine of x, okay, so this will be cosine of x, and the derivative of e to the x, again, this is reflexive, so this will be e to the x. So for y sub 2 prime, okay, so we have e to the x times the cosine of x plus e to the x times the sine of x. And carrying out to what we have with the second order derivative. Okay, so for e to the x cosine of x, okay, so you have e to the x times the derivative in x of the cosine of x, and reapplying the product property of derivatives. So you have the cosine of x times the derivative in x of e to the x. And guess what? We had worked with the derivative of e to the x sine of x, and doing this again. So taking the derivative in x of e to the x sine of x, okay, so you have e to the x cosine of x plus e to the x sine of x and again we have the derivative of the cosine of x is the negative of the sine of x. And again, the derivative of e to the x is e to the x. And if you notice, we have with negative e to the x sine of x and positive e to the x sine of x. You have these terms to cancel, whereas you have e to the x cosine of x plus e to the x cosine of x. And it's going to turn out that we have these two like terms in the middle to combine to 2e to the x times the cosine of x. So looking at setting y to y sub 2 and applying substitution, so we're going to have with a y double prime, so you have 2e to the x cosine of x minus 2 times in this case y sub 2 prime. So you have e to the x cosine of x plus e to the x sine of x. You have plus 2 times y sub 2 So filling in, okay, if you notice you have 2e to the x cosine of x, and then distributing we'll have negative 2e to the x cosine of x. So these portions will go out, and guess what? We're going to have negative 2 times e to the x sine of x plus 2 e to the x sine of x will completely cancel. So you have that 0 is equal to 0. So this is going to balance out. And so it does reaffirm that e to the x times the sine of x is a solution in y for this particular differential equation. Okay, now looking at solving for y, or in this case verifying what we have for y, and specifying what the value of the constant is going to be. Now we have an initial condition for this particular differential equation, y prime is equal to y plus 1, where we have at x is equal to 0, we have y is equal to 5. Okay, so looking at solving for the constants, and in effect, okay, solving for the specificity for what we have in the case of y. So you have for y, we have c times x e to the x minus 1. And we have that y prime. Okay, if I take the first order derivative of y, okay, so that's just going to be c times e to the x, negative 1 goes out. And we can verify. Okay, so you have y prime at c times e to the x is equal to y plus 1, so you have for y, again, you have c times e to the x minus 1, followed by the addition of 1. Negative 1 plus 1 will go out. C times e to the x is going to be equal to itself. And if I were to, I could actually stop here. But just like in the earlier verification by substitution exercises, okay, so you had that 0 is equal to 0. And so we do have that y equals c times e to the x minus 1 is a solution. Now looking at what we are going to have specifically for y, and ditto for the constant case, you have y of x is equal to c times e to the x followed by the subtraction of 1. So with y of x equal to c times e to the x minus 1. Okay, now again specifying what we're going to have for the constant. So we have x equal to 0. We had that y is equal to 5. So we have for y is at 5 whenever x is at 0. So you have 5 is equal to c times e to the 0 minus 1. E to the 0 is 1. 5 is equal to c minus 1. And we have for the missing constant value, okay, that is going to be at 6. So in the follow through, okay, with the value of the constant at 6, we're going to have in the results that y of x is going to be equal to 6 times e to the x minus 1. For number 22, okay, we're looking at verifying that y equals the natural logarithm of the quantity of x plus c is going to be the solution of this particular equation. Okay. So we have e to the y times y prime is equal to 1. Okay, so we have in the layout, okay, so you have y is equal to the natural logarithm of the quantity of x plus c. And if I take the first order derivative, okay, so you have x plus c has a derivative that just goes to 1, so no special kind of substitution is necessary. So for the first order derivative, that is going to be the inverse, the multiplicative inverse of x plus c. Now, looking at what we have in this equation, okay, so e to the y, that's going to be e to the natural logarithm of the quantity of x plus c. We have times y prime. Y prime we have again as the reciprocal of x plus c is equal to 1. Again, e to the natural logarithm of the quantity of x plus c, that goes directly to x plus c. And times the multiplicative inverse of x plus c. Left-hand side is going to go to 1, and that's going to be equal to the right-hand side itself. You have that 1 is equal to 1, so y is going to check out. Now for satisfying, what we have for y naught is equal to 0. Okay, so we have the general solution at y is equal to the natural logarithm of the quantity of x plus c. For y naught is equal to 0. Okay, so y is at 0 whenever x is at 0. Guess what? We've got 0 plus c is just going to be c. So you have 0 is equal to the natural logarithm of c. And getting out of the natural logarithmic notation and freeing up c, I can treat both sides as powers to which the natural logarithmic exponential base e is raised. Here we have e to the 0 goes to 1, e to the natural logarithm of c goes to c itself, and we have that c is equal to 1, and it's going to follow that for the full solution in y. As we transition from the general solution to the specific solution that satisfies y naught is equal to 0, we end up with y equal to the natural logarithm of the quantity of x plus 1.